Alright, so welcome to the fourth part of the momentum and impulse unit, where we're going to talk about the conservation of momentum, which you hopefully discovered in that last investigation, but here we're just going to go through it from a different perspective. So the conservation of momentum. Let's think about a situation. So here's a video clip of a baseball hitting a bat. So let's think about that situation, and so we're going to think about the impulse applied to the ball and applied to the bat, and the forces and everything in that situation. So if the impulse given to the ball is the force on the ball multiplied by the time of the bat, then we get this situation. Our first question, does the ball also exert a force on the bat? Well, we have to, because that's what Newton's third law says, equal and opposite forces. So absolutely, yes. How does the force of the ball exerted on the bat compare with the force the bat exerts on the ball? Again, Newton's third law says that it has to be equal and opposite. That's the only way. How do the two impulses compare? Well, the time in both situations has to be the same. So if we look at our equation for impulse, we get the same result of equal and opposite. So, and does the bat's momentum change as a result? Well, if there's an impulse applied to something, it's going to change the momentum of that object. That's what the impulse momentum theorem says. So absolutely yes to that question as well. So let's look at this mathematically. So we're going to have the impulse of the ball is equal to, now to make it equal and opposite, we just put a negative sign there and the impulse on the bat. Now we know that impulse from the impulse momentum theorem is also equal to the change in momentum on the ball, change in momentum on the bat. So we can carry this forward where we get P of the ball minus P O of the ball, and same thing with the bat. And this can actually be rearranged so that we get all of our initials, all of our P naughts on one side. So we get P naught of the ball plus P naught of the bat is equal to all of our finals on the other side. And this tells us a really interesting thing about when things are colliding and what happens. And this equation tells us that our total momentum before is equal to their total momentum after. And that's a very, very useful thing. And that's something that has been proven to be always be true. And that's again what you saw in the different types of collisions in that investigation. The total momentum before is always going to be equal to the total momentum after. So we'll come up with some different examples. We've obviously talked about baseball, so that's one. But we'll come up with some more examples in class of where we see conservation of momentum. So we have to remember that a system is only the objects that are interacting with each other and no other objects, and the only other forces that can be involved are the ones between those two objects. If there's other forces, the conservation doesn't hold nearly as true just because there has to be no extra force. So in this case, we have P of ball A and P of ball B. So we just go to A's and B's for this notation, and we also use the symbol prime to indicate our after ones. So slightly different notation for conservation of momentum, but just avoids having a lot of subscripts. We can put in MV, where we have MA, VA, MB, VB, and our after would be MA, VA prime, plus MB, VB prime. Doing these problems, one thing you're going to notice very soon is how much writing you're going to have to do. And there's really just no way around that because there's so many different variables. So let's take a look at this example here where we've got one car rear-ending another car and then they stick together afterwards. So we're looking for the speed that they're going afterwards, and we have to say that the two speeds will be the same, and that allows us to simplify our equation. So our starting point's always going to be the same, and it's going to be a lot of writing it out of MA VA and BVB is equal to MA VA prime plus MB VB prime. Now, one thing that we said is that the two velocities are the same on the other side, so what we can do is we can factor them out as one velocity so that we get MA plus MB, and that's just because they're equal. So that's not something you can do in every problem, but only in a situation where they stick together afterwards. That allows us to easily rearrange for our final velocity, where we get MAVA plus MBVB all divided by MA plus MB. Now we can plug in our numbers here, and again, it's a lot of writing, and there's really no way around it just because there's so many variables. 1,875 kilograms, 23 meters per second, and 1,025 kilograms and 17 meters per second, all over 1,875 kilograms plus 1,025 kilograms. And you put that in your calculator, and you're going to come up with a final velocity of both cars that are moving together because they stuck together of 21 meters per second. So one of them actually ended up going faster, so the one moved faster and one slowed down. And so that's you know, what you tend to see depending on the masses of the objects. One's going to speed up, one's going to slow down. Sometimes they'll come to a stop, sometimes they're going to go in the opposite direction, but we can always use the conservation of momentum for any types of collisions. So let's take a look at a couple more examples here. So we've got an astronaut at rest in space. And he fires a thruster pistol which expels hot gas, and that actually would allow an astronaut to move in the opposite direction. So how fast does he do that? Starting point's the same equation. We have to make sure our masses are in kilograms, but one thing to keep that we have to pull out of this one is the at rest. Initially, both objects are at rest, so VA and VB are 0, so we can actually set both of these as going to 0, so our equation simplifies very nicely in terms of how much we have to write out. And I'm going to let you finish that problem, but I'll tell you that the answer should be that the velocity of the person is in the opposite direction, which will be the negative direction, and it will be a mere 0.36 meters per second. So hopefully, if you go through the work, you get that answer as well. Now let's take a look at the next example, where we've got a bullet that strikes a heavy steel ball that's initially at rest. The bullet bounces backwards in this situation. How fast is the bullet moving after the ball bounces backwards? So we're always looking at momentum questions involving a collision between objects or some separation between two different masses. So you always have to be looking for when that collision is happening in your problem. So we've got everything here. In terms of simplifying, it's always nice when things are 0 because it saves things. So our initial mass B, the heavy ball, is at rest, so all of that's going to go to 0. So then we're just left with a little bit less of an equation, and again we want to look for VB prime. So I'm going to let you do that, but I'll tell you that the answer that you should expect is 6.7 meters per second. So that's the positive direction. And hopefully, again, you get that answer. So you have those two problems to work on, and I want you to try any two of these. Do not worry about doing them all, because that's definitely a lot of questions there. There's 8 questions. So as long as you complete these 2 questions in the notes and any 2 of those, you'll be more than prepared for class, and we'll go over more problems in class, because it's just going over problems more and more will help you. And as always, physics is awesome, and that's another unit done.